Good afternoon, everyone. We are today starting on a slightly somber note because it is the last class of semester. We do have a fair bit to pack in. Don't worry, any material that we don't really get to, we're not going to emphasize on the exam because we know you won't have studied it quite as well. I'll also leave a few minutes at the end for a brief recap of what's going to happen with the exam and where we are going moving forward for your studies in computing or just for your enjoyment of algorithms. Unfortunately, we're not going to have time for a full review session because we are a little behind, but more on where you can get a review later in this class. At the end of last class, we had developed a framework for looking at and considering a bunch of different algorithms. And we talked a little bit about complexity theory. Remember the discussion of P equals NP that happened at the end of the first lecture this week. Complexity theory allowed us to analyze algorithms of all different sorts: deterministic, non-deterministic, which are our random algorithms, and even quantum algorithms, which we don't talk about in this course. However, if you do want to learn more about, there is an incredibly interesting class offered jointly between physics and computer science that I highly recommend, and for which the head tutor is Alex Zabel, who is the same Alex from our tutorial staff here. Our problem for today is going back to our old Hamilton tickets. And if you remember, Bosch-Young suggested that the fairest way to distribute Hamilton tickets would not be by who arrived first in the line, but by who in the line had achieved the highest grade in FOA. And so we're going to take that suggestion a little bit more seriously today and see if we can come up with a data structure that allows us to do this. The basic setup for our problem is the same as before. People lining up early in the morning to get their Hamilton ticket. Some people might leave the line at some point from the front once the window opens and it's their turn. But in this instance, we are now giving people a priority in the line equivalent to their grade. So if there's a line of 10 people and a new person comes to the line and their grade is higher than everyone but the first person in line, they should get the second ticket. So that's our setup. We'll remember that. But now our question is, what kind of data structure should we use to best represent this scenario? Would a queue work as an abstract data structure the way we've defined it before? And if so, how would we use it? And if not, why isn't it an appropriate data structure for this scenario? Okay, what was your name again?
Jensen.
Jensen, okay. So Jensen, for this new problem with certain VIP students who get better grades, would a queue work or do we need something different?
Yeah, we definitely need something different.
Do you have any ideas of what kind of data structure we might want and how it would behave? What are the key operations that we need our data structure to be able to do? And make sure to hold the microphone up properly.
Yeah, we need a operation that we can insert element in between.
So we need to be able to insert someone. What else do we need?
Remove someone.
Remove someone and maybe check if it's empty or not. That seems like a pretty good pattern. And then when we insert someone, do we want to explicitly say where to insert it, or is there another way that we can describe how it should be inserted?
Yeah, if we can specify the position, that would be good.
So specifying the position requires us to know ahead of time where in this data structure the person should go. But we don't automatically know where their score fits in the set of all scores. So if you were going to describe our insert operation, not in terms of position, what might you describe it in terms of?
Index?
No, not the position. We know 2 bits of information about the person lining up. We know their grade and we know their name. And we are assigning them a position based on their
grade.
Based on their grade. So our insert operation should insert
based on the grade.
Based on the grade. Okay, so we have an insert operation that automatically puts someone in the correct position on the basis of their grade, or the basis of their priority, we will call it. And then we have an operation that removes someone from the front of the queue. And we're going to call this data structure. Any guesses? If it gives people a priority?
Priority queue.
A priority queue, very good. Can we have a round of applause for Jensen for helping us out? So Jensen's right in that we need these 2 different operations in order for our priority queue. And just like we've learned before, it is an abstract data structure, which means we could probably implement it using a bunch of different tools. Maybe a linked list or like a tree is the best way, maybe an array is the best way. way. We'll get to that in just a moment. We have our 3 different operations. Our first operation just tells us if there's anything in it already or not. Our second operation takes 2 arguments, the item we want to insert and the priority with which it should receive. And in our example, the priority is going to be the grade, and then our remove operation, which allows someone to get a ticket from the front of the line. We could try implementing this using a binary search tree, and then every time you wanted to insert something, you just insert it to the right place in the tree, and when you want to remove something, you go through the binary tree and look at all the items and pick out the one that is the largest. But with a binary search tree, if we're going to pick out the largest one, that's going to require us to navigate the tree pretty substantially, and we're not going to be able to pick out the item right away. It would be a whole lot better if the largest item were always the first one that we looked at. Let's see if there's a way we can do this. Yeah, so as I was saying, for our binary search tree, our insertions on average and worst case take log n, which is the height of the tree. If we want to find an item and we know the number of the item, the value of the item, it's going to take log n. And then creation and deletion is going to take n log n and log n respectively. Let's see if we can improve on this for our set of 3 operations that we have. So we could represent our priority queue using a heap, which is another abstract data structure. So in this way, you can see that we have layering of abstractions. One abstract data structure that's our priority queue is built using a heap. That's another abstract data structure, and we'll tell you what that is in a minute. And then a heap we can build using one of our basic computer science tools. In this case, we're going to do it using an array. This is what a heap looks like. It's very similar to a binary search tree with one slight difference, which is what is the rule about the relationship between a parent node and the children node. And in our case, we are going to represent the heap using an array, and that's the way we're going to implement it. So the heap is implemented using an array, and the priority queue is implemented using a heap. And so at the end of the day, the priority queue is implemented using a... This shouldn't be a hard one. Priority queue implemented using a heap implemented using an array, so therefore the priority queue is also using an array at the end of the day. So our max heap rule is going to be that our parents are larger than all descendants. We could also have a min heap, which is the opposite. If we wanted to award tickets to the people with the lowest grades in FOA, and I'm sure some of you are hoping that we allocate tickets to Hamilton that way, we could just reverse this and make the parent smaller than all the descendants. For our examples in today's class, we're going to focus on max heaps. If you want to try out the opposite, feel free. It's very, very similar. You just kind of switch the comparison in every place it occurs in the array. We could also compare our max heap rule to our binary search tree rule. For our max heap, it's the parent is larger than all the descendants, whereas the binary search tree is a much stricter ordering. It's that the right child is greater than or equal to the parent, which is greater than the left child. And so this means if we want to build a binary search tree, it's probably going to take us a lot more effort than it would take us to build a max heap, because the max heap is more lenient about where items can go in our data structure. So for our array representation of our heap, we're going to have a fairly simple rule. We're going to define in the array that for an element I, the 2 children of that element I, the 2 children that come off it, like just like in a normal tree, are going to be at locations 2i plus 1 and 2i plus 2 in the array. And the parent, similarly, is going to, if you follow the rule above and just reverse it, the parent of an element is going to be, for element in location I, it's going to be at location I minus 1 divided by 2. One very nice property of designing, of using a heap like this, is that a heap is actually going to produce a balanced tree. That is, if you can imagine a tree with all leaves on one side or lots of the leaves on one side, that tree is going to get heavy and fall over. What we mean when we say a balanced tree is that all the leaves are perfectly aligned so that it would be balanced unless there are some leaves that are still yet to be added on one side. So it's going to be balanced except for the addition of a few nodes that aren't there yet, but when we add them, they would help finishing out balancing the tree. This is our build heap code. Whoop, I skipped one slide too many. This is our build heap code and our sift down code. These are two key operations that we're going to need for our heap, and we will step through these with the help of our iPad actually drawing some of them out. So build heap is going to use this sift down operation, and for all the elements that you have, perform the following operation, put the just sift down the element. Now, what does sift down do? Let's see on the iPad, and that'll be the easiest way for us to understand it. So here is an example an example heap. And what we want to do is we want to remove one of the elements from it. So let's say we are removing 323. I've taken out 323, and now there is an empty space. This is no longer a heap. We need to fix it up. So what do? Well, we take the leaf over here that is the furthest one down the tree. So if we go all the way down the tree to the bottom and look at the furthest one along, so we're not looking at 66 because 66 is an earlier element. The last one in this tree is 111. And then what we do, we just put it at the top. Once we've put it at the top, we now need to move it down into the right place such that our heap property is preserved. Because as it is now, this no longer obeys the heap property. And so what we do is we compare 111 with 282. Is 282 bigger than 111? Yes, so swap it. Now we have to compare 111 with, now we have to compare 111 with 222 to make sure that we are still in the right position. Turns out we're not. 222 is bigger than 111, and so we put it in there. And now we have restored the heap property. If you look at every level, the parents are larger than the children once more. So that's our sift down. What about sift up? Can we do the same thing for inserting an element? Here is sift up. We have a partially constructed tree. Let's just move that line away. And we have a new element 441 that we want to put in. Well, the obvious place to put it to start with, is at, there we go, this will work. The obvious place to put it to start with, finally, is as the last leaf of the tree, in the place where there is room for a new element. But now again, we have violated the heap property. We can see that 441 is larger than 111, and this violates our max heap rule. So what we do is we compare it to its parent, compare it to the parent, and if it is larger than the parent, we swap it. Now we have to do it again because 441 is bigger than 323, and so we do the same thing again. We swap it. Now let me just reverse that so the slides are all fine for next year. And that produces our completed insertion of a new element. These operations are pretty similar when we actually go to the code using the rules that we defined before about where the parents and the children are. You'll notice that in this case we've written it in a recursive fashion because at each level we repeat the same process. At this level, look at the current node you're at, look at its parents. If the ordering is wrong, swap them, depending on either sift up or sift down. This gives rise to a very simple algorithm, not only for building our heap for solving our Hamilton priority puzzle, but also for sorting. Because if you have access very, very quickly to the largest element in your data structure, if you simply pull off the largest element and fix your data structure, and pull off the next largest element and fix your data structure, pull off your next largest element and fix your data structure, you naturally end up with the correct order of all your elements from largest to smallest, from highest grade to lowest grade, because that's essentially what our queue was doing. As a new person was joining the queue, they would go into the correct position on the basis of their grade, and then if the person handing out tickets was to check the order of everyone, they'd be getting in order from largest to smallest. So this leads to our heap sort algorithm, which is exactly what I just said. Build the heap, first of all, build the data structure with all your elements, and then while there are still elements in the array, take out the largest one and then fix it. And that's pretty much it. That is pretty much it. A very simple sorting algorithm that relies on a more complex data structure. Now let's see if the demo gods are with us today. And I forgot to try it on this computer, but I did try it on the other computer. So with a bit of luck, 0.2. And we can see that heap sort functions hopefully as planned. We're not going to dig into too much of the code details. And it doesn't do too many copies per item. Even with sorted, reverse sorted, with uniform items, it actually does really well. And then with random items, it does somewhat in the middle. And let's try this against merge sort and see how it behaves. Oh, this is a little surprising. Merge sort does better. And why is this surprising? Well, heap sort, if we figure out its asymptotic running time, only takes O of n to build the heap in the first place, and then n log n to remove each of the n items, and then for when we remove an item, we have to fix the heap up, which takes log n steps. So n times log n, which gives us a worst case for heap sort of n log n, while merge sort, if you remember, we had some issues. We thought it might be a little slow, and quick sort was even slower still. And yet what we've revealed with our actual execution of our demo code is that despite our asymptotic analysis for heap sort being really good and our asymptotic for quick sort not necessarily being as good, and same as merge sort, regardless, when we actually apply it on real test data, it seems that heap sort doesn't perform as well as merge sort. This is another illustration of the point which we've now gone over a few times, is that the practical runtime of your algorithm may differ from your expectations based on the asymptotic worst case or average case when actually applied to real elements. This does not mean that asymptotic analysis is not valuable. It just means that it's only one component in the analysis and design of algorithms. Now, Claire comes up to the ticket office. She got a ticket for Hamilton as part of the grand sorting, but she can't remember her seat number in this case. So the question is there an efficient way for the person at the ticket desk to build a data structure that allows her to very quickly figure out what someone's seat number is when they come to her? Assuming that the people are coming in a random order, it might be Claire, and there might be Hanny, and Yara might come at some point. They're not coming in the same order that they bought their tickets, but we still want to look up what particular seat number was allocated to them. Well, one way we could do it is we could have a really big table, maybe a table of structs, that matches people's names to their seats. And we could do a linear search through it and check, okay, is the person in front of me Lou? No. Is the person in front of me Dougal? No. Yes, the person in front of me is Claire. Okay, and the struct has her seat number is 82. How long does this algorithm take to find a person on average? Takes, the runtime is on average case O of n, and in the worst case also O of n, because it might happen to be the case, just like in this example, that the person we're searching for is at the end of the table. Can we do better? Well, whenever I ask this question in the class, the answer is almost always yes. The key idea here, is to convert the key, which is the name of the person, the thing we're trying to look up, into an index of the array. So one way to do this was if we know the order of the people that are coming to us, then we can just give them that order. So if the first person to buy a ticket would be person 0, and the second person was person 1, and the third person was person 2, that would be very easy. We just have to ask them, what order did you arrive in? And then we can go right to that position in the array. But this isn't really how ticketing systems tend to work. I mean, yeah, we could lay it out like this, but we need some easy way of going from a person's name to the index to their ID so that we can figure out where in the array they should be. We do have a way of doing this that doesn't rely on remembering the order in which they arrived, and this is called a hash function. It's a method of converting a large piece of data, such as a person's name, into a small piece of data like a number, and in particular, we will use special hash functions that are bounded within the range of our array. So if our array has room for 500 seats, we are going to set up our hash function so that it returns us a number between 1 and 500, or 0 and 499 if we're zero indexing. So for a key A, which our key in this case is going to be the person's name, use a function h of A to produce a value t, and t is going to be our new array index, and t should be less than the size of the array, and this is accounting for zero indexing. Then store the value corresponding to A at index t. So if A is the person's name and their seat number is 72, find out what index in the array that, let's say it was Claire. We put h of Claire, what might be ID number 3, and then store Claire's seat number 78 in index 3 in the array or in our data structure. This is called a hash map, a hash table, or even kind of a dictionary in Python. A dictionary in Python is using a similar kind of idea. You are hashing your key to produce some index, which is hidden behind the scenes, that then maps to a value. So essentially, a hash map or a hash table allows us to do what we call a key value store. We match keys to their values. We match names of people to their seats. But there's a trap. What if the location T is already occupied? There are a lot of names out there, and maybe we only have 500 seats. What happens if we've accidentally sold, what happens if two people, when we use the hash function, end up getting the same ID? What do we do then? Well, there are a few different options. Option one is we could just look at the next empty spot in our array. That's okay, but it ends up getting pretty complicated fast, as you'll need to remember how many spaces you skipped for the new person in order to come back to them later if you need to remove them out. And this will overall complicate the coding for our structure. Option two is we can, if any of you know a bit about the cuckoo bird, you know about their eviction strategy from their nest. It's a little unpleasant. I would suggest if you want some disturbing nature documentaries, go and look up the cuckoo. And so in honor of the cuckoo bird, we have named a hashing strategy, which is kick whoever is in that position out of the nest, out of their spot in the array, and then have a second hash function at the ready and put them in a new position based on the output from that second hash function. And you might ask, well, what if there's something at the location of the second hash function as well? Well, you could do cuckoo hashing with 3 or 4 or 5 hash functions, but then you need to have a whole bunch of hash functions, and managing it can also get a little complicated. This is a viable strategy, though. And strategy number 3, separate chaining. So if two people are matched to the same location in the hash table, if when you run the hash function over them, they both get the same ID, well, you could just store them at the same place, except at that place, instead of leaving room for a single item, you could store a list at every possible location. One particular thing that could happen, though, is if you get lots and lots of people that are all hashing to the same location, and hopefully this won't happen, hopefully your hash function is nicely distributed over the space, but if your hash table is small and your hash function is mapping a lot of items to a small space, you could actually get O of n worst case lookup time, because you'd have to look through n items all at the same spot. But overall, the really nice property of the hash function, of the hash table, remember it's also called a hash map or a dictionary, the very nice property of this is it only takes O of 1 to feed something into the hash function and get back their ID. And then we know that it's O of 1 to look at a given index in the array. We're only looking at one spot, and that one spot that we're looking at is the index returned to us by the hash function. So hash functions give us pretty fast insertion and very, very speedy lookups, which is pretty unique among most of our other data structures so far. This is our last abstract data structure, and I have prepared the table so you can compare it to the other data structures. Again, this doesn't mean that hash maps are better than the other data structures. You saw that heaps also had pretty fast pulling out the maximum element, and doing that in a hash table would be pretty difficult. But it has got great performance for a very particular set of operations that do really get used quite frequently. Out of all the data structures you've learned in this class, my guess would be that this one might actually be the one that you use most frequently, other than arrays, which form a real substrate for things. So remember this one and come back to it later. And that, I am glad to tell you, takes us to the end of the material for our course. That is it. You're now all algorithmic masters. You can go home. You can send a letter to Alistair saying, you know what, we don't need you anymore. I am the new professor of algorithms. You're done. Well, not quite. There's still a little work to go. We do have our main takeaway from the class, which is that designing algorithms requires careful thought. And there's still a lot to learn about the best way to tackle different sorts of problems. However, the base skill set that you've acquired in this class is the same one that you'll be using as you go forward, whether it's to another computing course, whether it's to applying some of these lessons to the field that you go into, or whether you've just taken this class for pure enjoyment. The key kind of thought process that you need to go through when designing and choosing an algorithm is, what is my problem and what are the constraints? Figuring out your constraints is often a really big, important part of designing or choosing an algorithm. Remember the Fibonacci question. We went through all these complicated and fancy mechanisms of calculating the nth number in the Fibonacci sequence, only to realize at the end that because of our constraints on a real computer, the best solution was just to write in the answer ahead of time and ask for it back later. So this is, I think, one of the main lessons that you should take away from the whole class. Once you've gone beyond defining your constraints and making sure you've identified your problem correctly, you want to ask, what are the theoretical characteristics of the solutions that you're considering? What is the asymptotic runtime? Match that against your constraints. Does it work out? Yes, no? And then, what are the practical characteristics of your solutions? So you might go and actually run a little test on one of the data structures. Have I chosen the right data structure? Is the performance on the real-world data that I'm feeding it what I would expect from the asymptotic analysis, or is it performing a little better than I might expect because of some feature or some distribution in my data that actually makes a certain choice better? There is also a second main lesson from class, and you'll probably be quite unsurprised at this one, and that's algorithms are fun. And that concludes all the content. So a few messages before we wrap up. The first is, please complete the end of semester survey. So Janjong is a little older and more advanced than me, but I am still a very, very baby professor. In fact, they don't even give me the title. But if you want to see me in more classes for you, perhaps in more classes later, or you just like what happened and want me to keep my job, please fill out the end of semester survey. I do not get to keep this job unless I get good scores. And so the more wonderful feedback we get, the easier that is. In particular, not only the rankings are helpful, but the comments are particularly helpful as well. So then I can take my little notepad to my manager and go, see what Albert said? Albert said, best professor ever. Don't let him go to Mars. So fill out the survey. Where to from here? What's next? Well, if you want more algorithms, here are two subjects that I recommend. Comp 207 if you're feeling nice and confident, but that's only offered in semester 1, so you might have to wait a year. You could put in some other computing subjects in the meantime. Or I did African drumming and dance and world music choir, and I highly, highly recommend both of those subjects as well if you need something to help fill the time between now and when Comp 207 is offered. Or if you're feeling that, this pace was perhaps a little much, but I still want to do a bit more algorithms, Comp 203 overlaps a bit with FOA, but still keeps you advancing forward. In particular, if you've enjoyed this class as well and you're not a computing major, I'd encourage you to consider a diploma of computing. This gives you more slots in your study plan and would allow you to take more computing without sacrificing the other work that you're doing. I did a diploma in my undergraduate. I was not, in fact, a computing major. I was a physics major with a diploma of music and then a diploma of computing. And so I highly recommend the diploma method for getting the most out of your undergraduate education. And plus, there's no rush. You don't get any benefit for finishing in 3 years, really. Just ask Liam. He's taken his time with his degree, too. Yeah, I think, how long did it take me? I think I finished in about 4 years, and that was a very good decision. A few details on the exam. It is going to cover pretty much everything in the course unless otherwise marked. However, emphasis on the exam is going to be loaded on particular areas. We are testing more of your programming skills than your analysis skills, and we are going to cover a lot of the ideas about designing algorithms are also going to be covered. We'll have more on this soon. In particular, we'll put up some slides with some more information. We'll have not the presentation slides, but the review slides will have a little more on this. We'll have a sample exam out for you, and that should be helpful. So a few notes on getting ready for the day of judgment, as we'll call it. Sit the exam even if you think you're not in a position to pass, because if you do well on the exam, that allows us to help make a case for why you should pass the subject, even if you've been struggling earlier. So if you think, oh no, I haven't met the hurdles, I should give up now, that's not true. The university hates it when students fail, and we personally also like to see you succeed. So we will use every possible opportunity to try and help you pass. So if you're worried, sit the exam, do your best. We will try and release assignment 2 grades in time so that you can get a little feedback there. There will be more office hours. I might do some public ones if I get a chance. Eat, sleep, and exercise because you're no use to anyone if you're not functioning, and there will be a sample exam. And with that, we've got one more thing before you go.
So we talked all night about the rest of our lives, where we're gonna be when we turn 25. I keep thinking times will never change. Keep on thinking things will always be the same. But when we leave this year, we won't be coming back. No more hanging out cause we're on a different track. And if you got something that you need to say, you better say it right now cause you don't have another day. Cause we're moving on and we can't slow down. These memories are playing like a film without sound. And I keep thinking of that night in June. I didn't know much of love, but it came too soon. And it was me and you, and then we got real blue. Stay at home talking on the telephone, and we would get so excited and we'd get so scared, laughing at ourselves, thinking life's not fair. And this is how it feels. As we go on, we remember all the times we had together. And as our lives change from whatever, we will still be friends forever.
And hopefully you can hear me.
And we make the big money when we look back now. Will our jokes still be funny when we still remember everything we learned in school? Still be trying to break every single rule. Will little brainy Bobby be the stockbroker man? Can he ever find a job that won't interfere with the tan? I keep thinking that it's not goodbye. Keep on thinking it's our time to fly. And this is how it feels. As we go on, we remember all the times we had together. And as our lives change from whatever, we will still be tomorrow like we think about now? Can we survive it out there? Can we make it somehow? I guess I thought that this would never end. And suddenly it's like we're women and men. Will the past be a shadow that will follow us around? Will these memories fade when I leave this town? I keep thinking that it's not goodbye. I keep on thinking it's our time to fly. As we go on, we remember all the times we had together. And as our lives change from whatever, we will still be friends forever. As we go on, we remember all the times we had together. And as our lives change from whatever, we will still be friends forever. As we go on, we remember all the times we had together. And as our lives change from whatever, we will still be friends forever.
Thank you so much. Yeah. Please, everyone, stay in touch. It's been such an absolute pleasure getting to know all of you. It would mean the world to me if I get to hear from you in a few weeks, in a year, in a few years, 10 years down the line, whenever it is. I would absolutely love to stay in touch with all of you. Thank you very much, everyone. Thank you for the flowers.